discuss how to define Mobius transformations and further topics related to it. Suppose you are having a domain, call it the set plane, and you're having a point in the domain Z, and then suppose if S is the map from this domain, and this S maps Z to the point S of Z is equal to AZ plus B divided by CZ plus D in the W plane, which is the range, then we call the function S to be linear fractional transformation. Suppose if we give a further condition to this linear fractional transformation, which is if the constants involved in the function which are a, b, c and d are such that ad minus bc not equal to 0, then the map is in turn defined as Mobius transformation. So in order to move further, we'll just see some among the problems which will give insights to this definition. So suppose in the first question which we have to solve, if you are given the Mobius transformation S of Z, you have to find S inverse of Z. Or if suppose you're given a point in the image set, you have to find the pre-image. So that is basic calculations. You can work on that and find what is S inverse of Z. And then after finding S inverse of Z, you have to prove that S of S inverse of Z is equal to Z, as well as S inverse of S of Z is equal to Z. That is, we are aiming to prove here that S and S inverse are really inverse mappings of each other. So that is the first question. The second question is also a simple question which you can prove very easily. Suppose if you are given two linear fractional transformations S and T, prove that their composition S composition T is also a linear fractional transformation. For that, in order to prove, just take S of Z is equal to AZ plus B divided by CZ plus D and T to be some alpha Z plus beta divided by some gamma Z plus delta, and then find the composition and make the composition, the image of that map in the form of a linear fractional transformation. That's it. That's a simple calculative proof. The third question is, suppose if you're given all the set of Mobius transformations possible in the complex plane and you're given function composition as an operation among these Mobius transformations, which are maps, will this form a group? A group is a basic algebraic structure which we see in abstract algebra, right? So you have to check whether the set of all Mobius transformations along with the operation function composition form a group. So what all things you have to find? You have to say that two Mobius transformations, when we are considering the composition of them, that should be a Mobius transformation, which is a binary operation. That means function composition is a binary operation. You have to prove that. The second one is the identity map should be a Mobius transformation. You have to prove that. The third one is that suppose if you are having a function to be a Mobius transformation, then the inverse transformation is also a Mobius transformation. You have to prove that. And then obviously composition of functions is associative, so you can just mention that, no need to prove that. So those four conditions will make us conclude, if these four conditions are satisfied, we can conclude that the set of all Mobius transformations under function composition is a group. So you have to work on that. These questions are all Small questions and their calculations are very easy. So work on that. Now, as we move on into these sessions, every linear transformation we consider is treated as a Mobius transformation. Suppose if we are not choosing it to be Mobius transformation, we'll particularly mention that. Okay. Suppose S of Z is equal to AC plus P divided by CZ plus D is given. It is a Mobius transformation. And if lambda is not a complex number, I am multiplying the numerator and the denominator with lambda. So you are getting lambda A into Z plus lambda B divided by lambda C into Z plus lambda D. That is the same as S of Z. That means for a particular Mobius transformation, the values, the coefficients we use A, B, C, D need not be always unique. You can think about multiples of them like this. So it need not be unique. And for this particular condition of uniqueness, you have to work on question number 20 in the exercise section. That is our workout for question 4. Okay. Now let's move on. Suppose the domain of SBC infinity. S is nothing but our Mobius transformation. So S of Z, we know it is this, and I'm going to take this Z out, and for in order for the moving forward, we need to take the Z sets out from the numerator and the denominator. I'm just cancelling, assuming that it is not equal to 0. Okay. And that is nothing but A plus B into 1 by Z divided by C plus D into 1 by Z. So suppose if I am taking this Z to tend to infinity. Z is taking the value infinity because we are thinking about the domain of S to be C infinity. That means the extended complex plane, it indeed have infinity. So when Z is tending to infinity, definitely 1 by Z will tend to 0, right? So that is an observation here. Z is tending to infinity. That will mean 1 by Z is tending to 0. Both are uh, the same. So here this 1 by Z will tend to 0. Here also 1 by Z will tend to 0, and that will give us A by C. So S of infinity is equal to A by C. So whenever we are putting an infinity to the Mobius transformation, its image will be A by C. Okay. Now just consider the complex number minus D by C. Okay, D and C are coming from the coefficients of the Mobius transformation, S of minus D by C. And you are doing the calculations. You can see it to end up to the value infinity, because the denominator you will have the value 0 coming. So that will mean that S of minus D by C is equal to infinity. That definitely means that S inverse of infinity is equal to minus D by C, or infinity is having the pre-image minus D by C. That means in C infinity you are having an image for infinity, as well as in C infinity you are having a pre-image for infinity. So S is mapping C infinity onto C infinity. That means infinity value is taken. Another note you have to think about is if A equal to 0 equal to C and D is equal to 0 is equal to C. This is not going to happen in any way, because for a Mobius transformation we defined that AD minus BC is not equal to 0, right? So if A and C are together becoming 0, that means our condition is not satisfied, as well as if C and D are similarly satisfying, both are equal to 0, then also our condition is being uh, turning into a contradiction. So this this will never happen, as well as this will also never happen. Now we are thinking about various particular cases of Mobius transformations. So the first case of Mobius transformation is called translation. It is nothing but if we are taking Z S of Z will be Z plus B. Okay. And in the form of the Mobius transformation we said earlier, it said it is AZ plus B divided by CZ plus D such that AD minus BC not equal to 0. So here A is turning to be 1, B is a complex number, C is equal to 0 and D is equal to 1. So we can observe that AD minus BC is happening to be 1, which is not equal to 0. It is satisfied. It is a Mobius transformation and it is called translation. We are calling it by a name because all these particular cases are really important as we move on. Okay. The next particular case is called dilation, and here if I am having a Z, S of Z will be A into Z for some fixed complex number A which is not equal to 0. So we can think about like we are kind of magnifying the image, right? Magnifying or making it very small, dilation. That's why like we can extend it and we can make it smaller. Okay. So here also you can find that A is a fixed number, B is 0 and D is 1 and C is 0, and it also satisfies AD minus BC, which happens to be A, and that is not equal to 0 by a definition. So the next particular case is called a rotation, which is nothing but Z, which is mapped to e power I theta into Z. The e power I theta will never become 0 because when we were uh, dealing with the exponential function, we said that exponential function will never take the value 0. So that is a particular case of dilation, as you can see that. And B is equal to 0 here, C is equal to 0, D is equal to 1, and AD minus BC, when you are calculating, you get e raised to I theta, which is never 0. So that is another kind of Mobius transformation. And the next one is called inversion. Inversion, by the name suggests, S of Z will be mapped to 1 by Z. And here we have A to be 0, B to be 1, C to be 1 and D to be 0. And here AD minus BC is coming as the value minus 1, which is not equal to 0. That is also Mobius transformation, and that is nothing but inversion. So 4 particular cases, important cases of Mobius transformation we came to know, which are translation, dilation, rotation, inversion. And we can just see a picture in which these are mapped, how how they behave when we are treating them in the Z and W plane. So you can see the translation first. So think about this rectangle here. A, this is origin, A0, call it ABCO. Okay. So when we are translating, what happens is it is moved to a place. See, with the magnitude modulus of B, it is moved like that. And for rotation, you can see this rectangle AOCB or ABCO is being rotated in a particular angle, and if we are taking it to be theta, that will be the theta angle rotation. And we said about dilation, here it is called magnification, both are the same. So here it is the value of A is taken to be 2, which is non-zero. So what happened is this rectangle ABCO is being made twice, 2 times the value of the x coordinate and the y coordinate, that becomes it becomes twice the figure here. And for inversion, what happened is you can see what is happening. This was A B C D and it shifted to the other quadrant, as well as it it is taking a smaller size. It has shrunken, right? So the explanation for that is given here. You can go through. Also, there it is given what does this inversion 1 by set do to a line, as well as what does this 1 by z, the map 1 by z do to a circle. So you can just go on through uh, work out how all these things happen for a good picture. So as a remark, we are having, suppose if s of z is equal to z, that means we are planning to find the fixed points of this Mobius transformation. So this is our Mobius transformation on the LHS. We are cross multiplying and just rearranging, you're getting the quadratic equation like this. That means if s of z is equal to z, we happen to get the quadratic equation. So for every point z which satisfies s of z is equal to z, that point should be a solution to this quadratic equation, and we know that a quadratic equation can have at most two solutions. So definitely a Mobius transformation can have at most two fixed points. So that is an observation we get from here. A Mobius transformation can have at most 2 points. And the next question is calculative question, which you can do too. Suppose if S is a Mobius transformation in C infinity such that the point A is mapped to alpha, the point B is mapped to beta, and the point C is mapped to gamma. Suppose if T is another map with the same property, that means A is mapped to alpha, B is mapped to beta, and C is mapped to gamma. Okay, then you have to prove that you have to consider T inverse composition S. You have to consider this map and then prove that A, B and C are fixed points of this T inverse composition S, and thus conclude that T inverse composition S is nothing but the identity map. These are all questions which you can easily work out. Please do work out these questions and see that you are getting a very reflective idea about Mobius transformations. And the next remark is, if 3 points and their images are given under Mobius transformation, it will be uniquely determined. That's what we are getting from this question. When you are solving this question, you get that if 3 points are given for the Mobius transformation and the corresponding images, if they are distinct, then from this question you will get T inverse composition S is equal to I, right? So that means S and T are the same. So whenever we are taking such a Mobius transformation, that will be unique. That's what we are concluding from there. Okay, the next part is suppose I am considering 3 points in the extended complex planes set 2, set 3 and set 4. The points are set 2, set 3 and set 4 in C infinity. I am considering two cases. Okay, in the first case, suppose if these 3 points are not taking the value infinity, so that they are definitely in the complex plane C. Okay, and in this case we are going to define S to be happening from C infinity to C infinity such that S of z is equal to set minus set 3 divided by set minus set 4, the whole divided by set 2 minus set 3 divided by set 2 minus set 4. This is a very important section you have to understand. Okay, here this S of z is equal to, suppose if this is 1 by set 2 minus set 3 divided by set 2 minus set 4, you can call it some m. Okay, suppose if this is m, this value 1 by, okay, so that means this S of z is nothing but 1 by m into set minus set 3 divided by set minus set 4, right? So this is nothing but mz minus set 3 divided by mz minus set 4. So it is of the form az plus b divided by cz plus d. Okay, so this is definitely a linear fractional transformation, and check out whether it is a Mobius transformation or when it will be a Mobius transformation here. Okay, so what we are talking about now is actually a fractional transformation. Okay, So we are defining s of z for those 3 points like this. Uh, no, not for those 3 points. If they are happening to be from C and they are not taking the values infinity. Okay. So the next case will be when they take the value infinity. So we are thinking that they are coming from the external complex plane. That means they can take the value infinity. So for that, for a better understanding, what I'm going to do is if set 2 is happening to be infinity. So what you do is just take this set 2 out from both sides like we did earlier and then cancel then the set 2 out. It is not 0, right? So that means in the braces you have here 1 minus set 3 divided by set 2, and this set 3 divided by set 2 will tend to 0 as set 2 is tending to infinity. Same here. Okay. So what you'll end up with is whenever set 2 is equal to infinity, the corresponding s of z we have to define it as set minus set 3 divided by set minus set 4, right? Similarly, when set 3 is equal to infinity, in the same manner take set 3 out and cross take the cross. Here it is division, right? So you take the reciprocals here and cancel out set 3, and here you know that set by set 3 and set 2 by set 3 is tending to 0 as set 3 tends to infinity. So you end up with s of z to be having the value set 2 minus set 4 divided by set minus set 4. Similarly, when set 4 is equal to infinity, in the same manner you can conclude that s of z is set minus set 3 divided by set 2 minus set 3. So these are very important calculations we obtained, definitions we obtained. That means we defined for set 2, set 3, set 4 coming from the complex plane. We defined s of z here, and similarly we define if they are coming from the external complex plane, we defined three of them, right? S of z is equal to this, s of z is equal to this, and s of z is equal to this guy sitting here. Okay, also there is a remark. If from the definition, if I am putting instead of z, I am taking it as set 2, the complex number set 2. When you substitute the value, you will get 1, and when instead of z, if you are taking it as set 3, then you will get 0. If it is set 4, you will get as infinity. So as earlier said, if we here have 3 points for this Mobius transformation and the corresponding images, and they are distinct, that means that this map is uniquely determined. What we defined now, we defined the map here, right? This one, the map here, this Mobius transformation is uniquely determined, and that is the only transformation with the property that s of z is happening to be 1, s of z2 is happening to be 0, and s of z3 is happening to be infinity. So in the next video lecture, what we will define is about cross ratio, which is linked to this Mobius transformation we just dealt with. So thank you for watching this video lecture, and do work out the problems which is mentioned in this video to understand a better version of what Mobius transformation is. So thank you again.